In this video, we're going to be looking at topic 3C, shapes of molecules, and this is part of the IAS chemistry course from Edexcel. So we're going to be looking at the principles of electron-pair repulsion theory. We'll be looking at bond length and bond angle, as well as specific examples of shapes and bond angles of compounds, and how we can use our knowledge of electron-pair repulsion theory to then predict the shape of similar sort of compounds. So electron-pair repulsion theory, or EPR, or sometimes even known as VESPR, because we add in valence shell, because we're only talking about the outer electrons, so valence shell electron-pair repulsion theory, states three simple rules. The first is that the shape of the molecule or ion is caused by the repulsion of electrons around the central atom. And we're talking about two different types. We're talking about bonding electrons, so those that are being shared, and non-bonding electrons, otherwise known as lone pairs. The second rule states that the electron pairs, whether they are bonding or non-bonding, are going to arrange themselves around the central atom so that the repulsion is at a minimum, or we have maximum separation. Okay, those are very key terms when you're answering any sort of bond angle or bond shape question, and we will talk about this later. And the third rule looks at the different levels of repulsion. So a lone pair repelling a lone pair is going to have a very high level of repulsion compared to a lone pair and a bond pair, which will in turn be higher than a bond pair. So if you've got a mixture of lone pairs and bond pairs within your substance, you're going to have your bonding pairs closer together than your lone pairs, because the lone pairs are going to repel more, because remember, they are all negative. And we'll look at how that affects the shape as we go through the examples. So the first two rules are used to determine the actual shape. So when we're talking about the number of electrons and how they arrange themselves, that's about the shape. And the third rule about the levels of repulsion is used to determine the bond angle. So we're looking at the shape and then the bond angle. Now, to determine the shape of a molecule or ion, we have to figure out how many bonding and non-bonding electrons are around the central atom. And the best way to do this is to draw out dot and cross diagrams. So you need to make sure that you are quite confident in drawing your dot and cross diagrams, and you can then determine the number of bonding pairs and lone pairs, and therefore the shape. Now, depending on these numbers of pairs, there are 7 possible shapes, and each shape has a bond angle associated with it. We're going to go through the different examples, and I'm going to show you the different numbers of bond pair, lone pairs, and an example of each and how we draw them. But the 7 possible shapes are linear, trigonoplanar, tetrahedral, trigonobipyramidal, octahedral, trigonopyramidal, and V-shaped. Now, you will actually have met quite a few of these already, you just don't realise that you have already met them. So let's start off by looking at the first one. So the first shape is a linear shape. And a linear shape, as you probably know the word linear, meaning a straight line. So linear happens when we have 2 bonding pairs of electrons and no lone pairs of electrons. So if we take, for example, beryllium. Beryllium has 2 outer electrons. So when those electrons are when we're drawing them in a dot and cross diagram, or we're thinking about their bonding, they are going to go on either side of the central atom because they want to be as far apart as possible. We're then going to bond it to a molecule of chlorine. And chlorine has its outer electrons, of course, but these are all bonding pairs, so they just stay separate from each other, and we're only looking at the actual pairs involved between the 2 atoms. So in this case, we're looking at 2 bonding pairs between the chlorine and the beryllium, and they want to be completely apart from each other, so we get a bond angle of 180 degrees. So remember, we want to have maximum separation or minimum repulsion. So they do this by arranging themselves at completely opposite sides. That is linear, and we could draw that out as that, just showing that the two bonds are going to be at opposite sides. Moving on to trigonal planar. Trigonal planar happens when we have 3 bonding pairs and no lone pairs. So we're going to use boron as an example here. Now for boron, if we have 3 bonding pairs, they are going to want to arrange themselves as far apart as possible. So we're going to get them in a shape like this. So they're going to be as far apart as possible, and we'll look at the bond angle in just a second. And again, we're going to bond it to chlorine. Now in a dot and cross diagram, we obviously have to draw out the chlorine's electrons as well, but they have no effect on the shape. We're only looking at the electrons around the central atom. And what happens now is we have the boron with the chlorines like this. Okay, we have that on our dot and cross diagram, and we get a bond angle here of 120 degrees, because we have obviously a 360-degree circle, and if we have 3 bonding pairs, to be as far apart as possible, we're going to split it into 3 120 segments. So each of the bond angles are going to be the same. Moving on to tetrahedral. Tetrahedral is when we have 4 bonding pairs and no lone pairs. And we can show this if we're thinking about our dot and cross diagram. So if we have carbon, we would draw a dot and cross diagram like this. If we had the carbon bonded to the hydrogen to make methane, you can see that we have 4 bonding pairs, and they form a tetrahedral shape. So we have the carbon in the center, and then this is where we have to start thinking in 3D. Both linear and trigonal planar are flat molecules. Now for tetrahedral, we have to think about 3D. So you may find that your teacher may use mods to help you understand this. So we have 1 hydrogen going up, 1 hydrogen in the same plane, and then we want to imagine that we have 1 hydrogen coming out of the screen and 1 hydrogen going into the screen. And the way that we show that is we use a wedged bond for coming out of the screen and a hashed bond for going into the screen. And each of these has a bond angle of 109.5 degrees. That is the tetrahedral shape. Moving on to trigonal bipyramidal, this is where we have something like PCl5. So we have phosphorus with 5 individual electrons this time, no lone pairs. Again, bonding, this time we're going to have it to chlorine, drawing in all of the chlorines. Now, of course, you don't have to draw the dot and cross diagram, but you may find it much easier to figure out the number of bonding pairs and lone pairs. So we get something like that. So we have 5 bonding pairs. Now, this is actually quite an easy one, because whenever you see a substance that has something like PCl5, as soon as you see the 5, you automatically should be thinking 5 bonding pairs without even having to draw the dot and cross diagram. And it has 0 lone pairs. And we call this shape trigonal bipyramidal. And what happens is we have the phosphorus in the center, and then above and below we have the chlorines. We then have 1 chlorine in the center, and the 3 that are in the center of the phosphorus are going to be in a trigonal planar shape. So they're going to be separated, and we have our wedged bond and our hash bond to show that one is coming out of the screen and one is going into the screen. So this time we have different bond angles. From the top to the center, this bond angle here is 90 degrees. But between the 3 and the center, this bond angle is 120 degrees. So we have to take into account the fact that we have two different bond angles. We have 90 and 120. And that's trigonal bipyramidal. For octahedral, this is a little bit similar, that as soon as you see the formula, like SF6, you should automatically be thinking octahedral, because octahedrals have 6 bonding pairs and no lone pairs. So if you have the sulfur in the center, you're going to have 6 sets of electrons, each bonded to a fluorine, to give you 6 bonding pairs around the central atom. Something a little bit like that. Okay, now that of course can become quite confusing when you start to draw it out, which is why we have the shapes that we're looking at here. So we have the sulfur in the center, and we have a fluorine at the top and a fluorine at the bottom. And similar to the trigonal bipyramidal, the rest of the atoms involved are going to be in the center, but this time they are going to be in a square shape. So we have 2 going back into the screen, and we have 2 coming out of the screen, like that. And every single one of these now, from the top to the center and between the centers, they are all at a 90-degree bond angle. The last 2 are slightly different, because this time we start to include lone pairs. So if we have trigonal pyramidal, an example of something that has this is NH3. So if we draw this out, we know that we have nitrogen as our central atom. We've got 2 electrons already paired, and then one more set of 1 electron in each of the 3 other spaces that can form 3 bonds with hydrogen. And we said at the very start that lone pairs are going to repel more than bonding pairs. So again, we need to take this into account when we're talking about our actual shapes. So the lone pair here is going to actually cause the bonding pairs to move closer together, and we get a shape that looks a little bit like this. So we have our lone pair at the top, we have 3 hydrogens at the bottom, 1 in the same plane, 1 coming out of the screen and 1 going into the screen. So we have 3 bonding pairs and 1 lone pair, and they have a slightly different bond angle, and we see a bond angle this time of 107, because the lone pair repulsion is going to be greater when it's compared to the bond pair repulsion. So it's pushing these bonds closer together. So rather than being the 109.5 like they are in tetrahedral, they become closer, and it is 107. V-shaped, again, very similar, where this time we have H2O and we have 2 bonding pairs and 2 lone pairs. So we have the oxygen that has 2 bonding pairs, and then it bonds to 2 hydrogens, so they have 2 bonding pairs. So you get something that looks like this. You can see that we're pushing the hydrogens closer together because the lone pair repulsion is quite large in comparison to the bonding pair, and this is then reduced, and we get a bond angle of 104.5 degrees. So Here's the summary of all our shapes. So we have the linear, 2 bonding pairs, and we have BeCl2 as our example. We have 3 bonding pairs as trigonal planar, and this is BeCl3. Of course, that could be any other halogen. For 4 bonding pairs and no lone pairs, it's tetrahedral, and our example is CH4 or methane. For 5 bonding pairs, we call it trigonal bipyramidal, and our example is PCl5. For octahedral, we have 6 bonding pairs, so we have SF6 as our example. For trigonal bipyramidal, we have 3 bonding pairs and 1 lone pair, and our example is NH3, but we could have any of the group 5 elements. This could be PH3, for example. And for V-shaped, we have 2 bond pairs and 2 lone pairs, and our example is H2O. We also look at the bonding angles, where we have 180 degrees for linear, 120 for trigonal planar, 109.5 for tetrahedral, 107 for trigonal pyramidal, 104.5 for V-shaped, and for trigonal bipyramidal we have 2, we have 90 and 120, and for octahedral we have 90 degrees, or we could even talk about the 2 fluorines being at 180 degrees from each other, but we'll typically only talk about the 90 degrees. So we can use our electron pair repulsion theory in an example question. So we've got 2 possible ways of arranging the bonding pairs and non-bonding pairs in XeF4, and we're showing the 2 examples here, and we want to suggest which of the 2 arrangements is most likely and justify the answer. So let's call the first one A and the second one B. So we want to be thinking about the shapes. Well, we know that we can see that we've got 4 bonding pairs and 2 lone pairs. Now this is an example that we haven't seen, but what we did see was we saw 6 bonding pairs, and we know that that made an octahedral shape, and that gives us the shapes that we see here. These are the basis of octahedral, but what we need to focus on is thinking about the repulsion. So we know that lone pairs are going to repel more than bonding pairs. So what we would see is this here would actually have a very large repulsion, and that's not the point in a bond shape. The whole point in a bond shape is to minimize the repulsion. So what we would actually see is we would see structure A, because the lone pairs are arranged to minimize repulsion. Okay, if you look at the lone pairs in structure A, they are 180 degrees from each other, rather than 90 degrees the way that they are in structure B. So structure A is going to be more likely because we are minimizing repulsion. Whenever you're explaining a bond angle, you should always be referring to minimizing repulsion. So we've previously talked about polar and non-polar bonds. We can now use this concept to tell us if we're going to have a polar or non-polar molecule. So we have this difference in electronegativity between the atoms, and we get the movement of our bonded electrons. For example, if we have HCl, we know that the electrons sit closer to the chlorine because the chlorine is more electronegative, and this becomes delta positive and delta minus. And we call this separation a dipole. So this polar bond is known as a dipole. And every single bond in a molecule will have some sort of dipole associated with it. And as I said, we call these polar bonds. Now, depending on the bond angles, individual dipoles within a molecule can either reinforce each other or they can cancel each other out. Now, what that actually means is if the dipoles cancel each other out, for example, one dipole is pulling to the left and one dipole is pulling to the right, they will cancel each other out and the molecule has no overall charge. For example, one side is not more slightly negative than the other. And we call this a non-polar molecule. And we will look at examples in just a minute. If the dipoles reinforce each other, for example, all of the dipoles show that the electrons all sit to the left of the molecule, then the left-hand side becomes slightly negative and the right-hand side becomes slightly positive. And this is reinforcing the dipole, and we call these polar. What's important to understand is that there is a difference between polar and non-polar molecules and polar and non-polar bonds. And we'll look at some examples now. So if we take a carbon dioxide molecule where we have a linear shape, we've got polar bonds because we have a difference in electronegativity, but the dipoles are pulling in opposite directions, therefore they are cancelling each other out. So carbon dioxide, whilst it has polar bonds, is a non-polar molecule. So overall, there is no charge or no difference in the charge distribution. For trigonal-planar, like boron chloride, BCl3, again, there are polar bonds because they have a difference in electronegativity, but it is a non-polar molecule because they are all cancelling each other out, and it's because the molecule is symmetrical. So if you have a line of symmetry, you're going to get a cancellation of your dipoles. So really, for a polar molecule, we're looking at symmetry. But when you're answering a question, don't just say because it is symmetrical. You have to say it's because the the dipoles are cancelling each other out. If we look at tetrahedral, again, tetrahedral has polar bonds because we have a difference in polarity between carbon and chlorine. But again, because it is symmetrical, the dipoles all cancel out, so this is a non-polar molecule. However, if we take the same tetrahedral shape, but this time we change it to trichloromethane, we're going to get a slight difference here. So again, we still have polar bonds because the carbon and the chlorine are going to have a difference in electronegativity. But what we see here for the carbon-hydrogen bond is that the electrons are pulled more closely to the carbon, meaning there is a lot of negative charge at the bottom of the molecule as opposed to the top, because at the top this is delta positive, whereas at the bottom this is delta negative because all the chlorines pull all of the electrons closer. We now have an overall dipole, and that's what this here shows, that we have an overall dipole, showing that we have a more negative charge at the bottom. So this is a polar molecule. Again, if we look at trigonopyramidal, so ammonia, NH3, we have polar bonds because the nitrogen and hydrogen have a difference in electronegativity, and this time they are all reinforcing one another. So all of the electrons are going up towards the nitrogen, giving the nitrogen a slightly negative end, whereas all of the hydrogens at the bottom are slightly positive. So again, we have an overall dipole, and this is a polar molecule. When we have water, we have H2O, and again, polar bonds between the oxygen and the hydrogen. And not only do we have lone pairs at the top, the oxygen is also pulling all of the electrons. So the top of the molecule becomes delta negative and the bottom becomes delta positive. So again, the dipoles are reinforcing one another, and this is a polar molecule. So if you have polar bonds, you can either have a polar molecule or a non-polar molecule. So this is where you have to look at the shapes. If you have non-polar bonds, so you have no difference in electronegativity, you can only have a non-polar molecule. So you have to have a difference in electronegativity, i.e. a polar bond, in order to get a polar molecule. So you're always looking at, first of all, is there a difference in electronegativity? And then second of all, looking at, do the dipoles reinforce one another? If they do, then it's polar, or do the dipoles cancel each other out? And then it is non-polar. This can be quite tricky, and it is very common in exams to mix up polar bonds and polar molecules. So please be very, very careful what you are referring to when you're looking at polarity. Be very specific if you're talking about the bond or the overall molecule. So let's have a look at an example. Well, we've got, first of all, H2S. So H2S is going to be similar to H2O. So this is going to be a V-shaped molecule. So you're going to have something that looks like that. You are going to get a difference in electronegativity between the sulfur and the hydrogen, and it's going to cause the electrons to be pulled closer to the sulfur. So we get a dipole towards the sulfur on both sides. This causes the sulfur to become delta negative and the hydrogens to become delta positive. So overall, the dipoles are going to reinforce one another and we get an overall dipole. So this is a polar molecule. When we look at CH4, well, we had that as one of our examples. This is a tetrahedral shape. And it's a tetrahedral shape that is symmetrical. So because it's symmetrical, although there are polar bonds in our dipoles between the carbon and the hydrogen, so going towards the carbons, it is symmetrical, so they cancel each other out. So this is a non-polar molecule. And for PBr3, this would be similar to NH3. So this is going to be trigonal pyramidal. So I've got the phosphorus with my lone pair, and I have my Brs. And I am going to get a polarity between the bonds. So these are polar bonds towards the phosphorus. And we see again, all of the dipoles are reinforcing one another. So I get an overall dipole, meaning that this is a polar molecule. So before you can determine the polarity, you have to get the shape correct. And then once you get the shape, you can determine, do the dipoles reinforce one another or do the dipoles cancel each other out? And therefore you can work out if it is polar or non-polar. So there's our answers. We had H2S is polar, CH4 is non-polar, and PBr3 is polar. And it goes into the same explanation that we just gave. So let's finish off by looking at some past paper questions. What you'll find in the old specification is that these are all in Unit 2, because this used to be part of Unit 2, whereas in the new specification, these are all in Unit 1. So just be aware that when you're revising Unit 1 using old specification past papers, there are not any bond angle questions. You have to look at Unit 2 for those. Your teacher will be able to help you with example questions or be able to tell you which questions to look for in the past papers. So iodine trichloride molecule is T-shaped, and we've got the shape here. Now this is a shape that we've not seen before, which is why they give us the structure. What we want to be able to say is, first of all, are the ICL bonds polar? And second of all, is ICL3 a polar molecule? And we want to justify the answers. So let's start off first of all with the bonds. So are the bonds polar or not? Well, yes, ICL bonds are polar. And the reason why is because chlorine is more electronegative than iodine. So the chlorine is going to pull the electrons closer towards them, and you could even draw a dipole. So we're going to get a delta positive and delta negative for each of the chlorines. Then we want to look at the molecule. So now we have to think about the dipoles that are present. So first of all, we can see that the dipoles on the left and the right are going to cancel each other out. However, the dipole at the bottom is not cancelled out by anything. So for the molecule, ICl3 is unsymmetrical, meaning the dipoles do not cancel. And when the dipoles don't cancel, it means that ICl3 is a polar molecule. It is quite a bit of writing for 2 marks, but you have to make sure you have your justification. If you simply say the bonds are polar and the molecule is polar, that does not give you the marks. You have to state why. So the bonds are polar because there's a difference in electronegativity. The molecule is polar because it's not symmetrical, or the polarities or dipoles do not cancel. Then we want to look at the shape of a nitrogen trichloride molecule, and we want to justify our answer. So if we think of the nitrogen, and we think about the bonds that are around it, the electrons that are around it, we know that we have a lone pair, and then 3 unpaired electrons. They are going to bond with the chlorines, and we're going to get a dot and cross diagram that looks something like this. And around my central atom, I have got 1 lone pair, 3 bond pairs. So the shape that is trigonal pyramidal. Now that gets you 1 mark. The justification then comes from the second and third mark. So why is it trigonal pyramidal? Well, it's trigonal pyramidal because we have 1 lone pair and 3 bond pairs around the central atom. And then the second mark comes from always stating the same key phrase every single time, is that the electron pairs arrange to minimize repulsion. You must talk about minimizing repulsion or maximum separation, but minimizing repulsion is the more preferred term. If you do not say that in a bond angle question, you will not get the marks, and you're just throwing away easy marks. And there's the mark scheme for those. Now let's finish off with one last set of questions. So we've got BF3, and we want to name the shape and then give the bond angle. So BF3, we're going to draw it out. So the boron has 3 electrons surrounding it, and it is then bonded to 3 fluorines, like that. So I have 3 bonding pairs that can only be trigonal planar, and then our bond angle for our trigonal planar is always 120 degrees. Okay, they're going to be marked independently between these points. So if you get the shape correct and the bond angle incorrect, then you can still get 1 out of the 2 marks, or vice versa. For NF3, suggest the shape, draw the shape that you would expect and suggest the bond angle. So this is very similar to the one that we just looked at. So we know that the nitrogen is going to have the lone pair, and then it is going to form 3 bonding pairs, and this time we want to draw out the full shape as opposed to the dot and cross diagram. So this shape is going to be our trigonal pyramidal. So the bond angle in a trigonal pyramidal is going to be 107, and then that's 2 marks, 1 mark for the shape, 1 mark for the bond angle, and we want to explain then the reasons why. So we want minimum repulsion between the electron pairs. Again, there's that key phrase. And then we have to just say why it's 107 in comparison to the 109, and it is because lone pair, bond pair combinations repel more than bond pair, bond pair. So we're getting this increase in our repulsion when we have this lone pair, meaning our bond angle here becomes smaller. And then lastly, draw a diagram to show the bonding in a single product between the reaction of BF3 and NF3, and then identify the type of bond. So we had a molecule that only has 3 electrons around its central, 3 pairs around its central atom, and we then had a molecule that had a lone pair. So when we have a lone pair and an empty orbital, hopefully you remember from topic 3b that gives us a dative bond. So we're going to get the nitrogen bonding into the boron like that, showing the donation from the nitrogen to the boron, and that is a dative covalent bond, and that's your 2 marks. There's the mark scheme where we have our 2 marks here, so 1 mark for the shape and 1 mark for the dative covalent bond. And that's everything for topic 3c, shapes of molecules. Again, as with other examples, I would strongly suggest that you practice these, and there are lots of examples within the textbook or within past paper questions, or of course ask your teacher. If you do have any questions, please feel free to leave a comment below, and we hope to see you back soon.